So hi, I'm Vincent Zimmer, part two, presenting with my colleague Giri Mudusuru, and we're going to talk about FSP 2.0. So like with Lee this morning, I'm going to sort of intro, and then Giri's going to sort of spiral into the details. So what was the intent of Intel FSP, and what are we doing here? So the idea is this is an effort to encapsulate silicon initialization that, very critical, SoC specific, something that, not readily open sourceable for IP protection or other things that if people were to change the code, bad things might happen. And so essentially FSP is a well-defined interface to a binary that you can include in many different environments. It has an API set, some interface code, and it has support for different parts of the SoC, like in this picture, the CPU, system agent, PCH. And the real point is allowing us to work with a lot of different communities, whether it's a Chromebook with coreboot, where ROM stage will orchestrate interaction with the Intel FSP, or an EDK2 style BIOS, where a lot of what's historically been the PEI phase will be subsumed in the FSP. Or we've even seen, like on the Bay Trail Minnow platform, Simon Glass just launched Uboot x86 directly from FSP. We think that's great in the sense of want to lower the barrier to have people do development on Intel-based platforms. So again, ease integration. When we say bootloader here, we're talking about the platform firmware, not the first stage OS loader, and working with open development communities. So as mentioned, FSP has a few external interfaces: Temporam init, FSP memory init, Silicon init, and Notify. With it's weird. It's sort of chopping off part of the deck here. The data, the input to it is data, and then the output are things called handoff blocks, memory-based data structures. And then, so why did we go to FSP 2.0? If you guys recall, in the 2012, circa 2012, there was Intel FSP. It was predominantly driven by our Internet of Things group. And so one of the challenges was each FSP instance was sort of different for each SoC, so the interface code had to be slightly customized. And so what we observed was, hey, easing development with open communities is great. Let's all work together on FSP. So Giri, myself, a lot of guys at Intel, we sort of took the existing FSP model, sort of locked down what we thought would have been architectural or consistent APIs, and we called that FSP 1.0, and then worked with the upstreams to have wrapper code, whether coreboot or EDK2, such there was only one interface. And then through some product development, there were some enhancements to FSP, what were called FSP 1.1. And now what the bulk of today's conversation is to really explain the intent behind why FSP 2.0. And Andre's talk yesterday talked a little bit about it. Booting from eMMC posed one challenge. So the original FSP, what became 1.0.1.1, had memory map structures near the reset vector. Well, what if you have a medium without memory mapped execute in place firmware? So there was a sort of an architectural dependency on the preceding FSPs, which motivated it. And then some learnings on using FSP, more modularity. Mentioned this dual FSP, but any security model where you may want to not have, say, memory in it in your read-only block, you may want to dual out some of the silicon flows, and then size inherent in that if you don't want to duplicate everything. Having each component with its own configuration data, and then some more reset flexibility. So what we believe is, we built the first one, worked with community, found issues, evolved the spec, in 1.1 where we ironed out some of those issues. And then 2.0, we observed these physics problems like the non-memory mapped boot. And again, building things. So sort of as we've evolved the 1.0 to 1.1 to 2.0, we've seen platform instances in the open, a lot of great examples, a couple Chromebooks. We have a couple EDK2 solutions based on 1.1. And now with upcoming silicon, you're going to see more 2.0. And speaking of silicon, I work in a software group at Intel. We sort of work with IoT client server. So I do software, but when it gets down to the details of hardware and the magic that's going on, we have experts like Giri, who's sort of the lead for our client silicon and firmware, and he's going to walk you through the rest of the presentation.
Thank you, Vincent. So as Vincent started the FSP 2.0, primarily it started as an extension. How do we support the non-memory mapped boot devices like the MMC? And as we started there, we also looked for things that we have learned during the 1.1 implementation. As Vincent mentioned, 1.0 versus 1.1 is 1.0 was the implementations, the embedded group, the IoTG side implemented. We logged that spec. We worked with Google and try to see how we can make it fit into this Google coreboot as an example, and also make it linear flow. We'll talk in the boot flow about what the linear flow, why we did 1.1, and made it flexible for the bootloader to do some of the stuff, in this case, coreboot. We also added the key thing is the reset flexibility. This is part of the learning, and before that, the data, static data, which is built into the FSP, also split into various components. So here is a high-level layout, how the 1.0 and 2.0, I'll walk through them. So if you see the first like 1.0 or 1.1, pretty much it's defined as the 5 APIs as we saw in the previous slide. And each phase, I'll just quickly walk through the temperaminate. The primary scope for it is to bring up the cache SRAM and do any early silicon initialization as part of that. So here, the naming of that is more of a phases. That's the bring up of the temporary RAM phase. In certain cases, like if you have a silicon with SRAM available, you may not need to even use that phase, but that can be considered as more as a early silicon phase where you need to do switching the processor modes and other things. The second one is the FSP memory init, which is the memory initialization or memory bring up phase, which is where we go, the DRAM init, detect, and all the initialization happens. The primary goal of that phase is bring up the memory. It does more than that. For certain reasons is like if you have to do certain programming before you lock certain registers, or you need to determine which features to be enabled, how the memory layout or allocation needs to happen. But the exit of that will be primarily is memory up and running and the interfaces, and reports the memory status out through the hubs to the bootloader. And the temporam exit is if you enable the temporam initialization cache SRAM, that is where we just tear off that cache SRAM. And silicon init is the rest of the silicon initialization that needs to be done. Here it is the uncore or the system agent features, or the PCH IO features, or bring up the boot devices and other things. And notify phase is where we leave certain things like the post PCI bus enumeration. There are 3 calls within that post PCI bus enumeration, and also ready to boot event. And we added one more called end of firmware. At these 3, where we lock certain registers or make sure that the chipset for security reasons and all other things, which we cannot lock prior to that because we want the bootloader to do whatever it needs to do, and leave that flexibility along that. And those certain register lockings will be done as part of the silicon requirements, not necessary from architecture. It's the placeholders. If we can lock everything and there is no impact to the bootloader, we could do it as early as possible. And when we started with that is the 1.1, we extended that the 3 FSP memory init, temporam init, and silicon init. In the FSP 1.0 implementation, everything was FSP init 1 API. We broke it down to give more flexibility for the bootloader and make it linear operation. And that's part of the engagement we worked with Aaron and Duncan to make sure that how we can make it a linear flow and also flexible for the bootloader to do certain stuff. And as part of the implementation in the ROM stage, RAM stage, and the Google's Chrome read-only model, in the implementation without changing the architecture. So the 1.1 is pretty much the usage model. We internally split that into two. Here we call FVs, which is a firmware volumes, which is internally two separate binaries, still packaged as one FSP, so that the memory FV is executed in the ROM stage, which contains the temporam init and memory init in that case. And the silicon FV is the one which will be in the updatable code. So you have the single FSP, but technically you have two FSPs. One piece of it is launched from the ROM stage, and you can use the other one from this based on the manufacturing mode or in the updatable mode. So we took those learnings, and instead of just being a use case of that, of the FSP 1.1, we made it architectural and also make it a flexible in the 2.0 while trying to solve the non-memory mapped boot model. Essentially group those into three different architecturally FSP 2.0 compliant image is technically three binaries padded together. We'll still distribute as a single binary, but there is a Python script we have already in the open source, so you can use that to split into three different binaries. And you get the flexibility of, instead of having like everything rebased in one location, based on the temporam phase could be run in the SRAM, and the memory code could be run in the cache SRAM while you're doing it, and the silicon code could be run from this. So you can, while you can do it post rebase, or while building it, you can rebase at different addresses in your memory map. You have that flexibility with the 2.0. So that's what the primary is. As you can see, the APIs are pretty much similar. It's more about how do we package that contents and make sure we give that flexibility. So here is the 2.0 boot flow. You can see in the representation that these are three individual binaries represented within the central FSP as a package. The key change from 1.1 to 2.0 is the FSP, if it needs certain things to be reset, if it finds something not configured properly, if it has to unlock, or if it is locked and need to unlock, FSP used to trigger the reset, which was limiting the bootloader if it has to do some housekeeping, like sending an EC command or doing something at a platform level. So we started initially as maybe we'll give a flexibility for the bootloader, then the bootloader calls back into the FSP for doing the reset. Then we ended up just, FSP will return if it needs a reset, it will return, hey, we are exiting this with a reset status, and the bootloader will read that and perform the reset sequence instead of putting everything in the binary blob, because reset is pretty much there. Reset could be customized based on SOCs, but we will be defining that as part of the integration guide, what bootloader needs to do with specific types of resets. Other than that, the boot flow is pretty much linear flow. The bootloader starts, and bootloader is the one which starts at reset vector. Treat this as individual three pieces of silicon initialization code delivered along with the silicon, which should be independent of any platform configuration or the usage. The primary scope and goal of that is, how do we build a, if you are using a silicon, if the FSP is meant to be that silicon initialization code, which should not limit you. If you can build a platform around it, this still should meet your requirements, and bootloader should have all the flexibility. Any questions? Maybe I can pause here. Yes.
Are any parts of this optional?
Yes, that's a good point. So as part of the FSP 2.0, we also made the temporam init and the temporam exit APIs as optional for a couple of reasons. One is there is a drive from the Google coreboot implementation that the temporam exit and init code, because it's pretty much generic, right? Bring up and tearing of the cache SRAM. Those can be implemented in public in the core bootloader itself without using this. Or in the future, if you have enough SRAM available in the silicon itself, then these APIs could be optional. So considering those two use cases, we defined those two APIs as optional. And based on that's what we put it as architectural in the spec itself, that based on the implementation, these two APIs can be optional. And if it is optional, we have handled that in the, how do we call the rest of the APIs that's part of the defined in the spec itself. So we'll quickly walk through the key changes, not necessarily getting into details, but the FSP Info Header, which is the key information which you hold in the binary. The parsing of the FSP is pretty much same as the FSP 1.1. The only difference, which I didn't capture in the slides, but the difference is in the earlier FSP implementation, the FSP Info Header is present in the bottom of the image or the starting of the image. And in this case, each component, as we described, the T, M, and S, the three phases, each will carry its own info header. So that means you can treat each one as independent FSP binaries. And the header, info header, will describe whether it is which phase of which component is it. So, and the changes are, we added a new field for spec revision. Earlier in the 1.x implementations, we had the FSP header revision overloaded with also the spec. That is, version 1 is 1 and version 2 is 1.1 spec. And we tried to do the same, like version 3 is like FSP 2.0. And we got a feedback from Aaron that seems to be confusing because it's not like, it's confusing like what header 3 is like FSP spec 2.0. So we defined a spec version field, which is a BCD value, which will at least give the major and minor version of the spec so that it's obvious and it's clear if you have to read it from the runtime or using tools. And also the header revision is updated, and image attribute, we had image attribute, which was used only for the GOP support, like whether FSP supports the graphics or display bring up or not, internal graphics. And we had that was the only one in the 32-bit. So we reduced that to a word and defined a component attribute in the other word, which will indicate the types of in the use cases, like whether it's a debug FSP or a release version, and also whether it is a official release versus a engineering test builds, because in this way, at least when you get a binary, it could be easily identified by the binary itself and not necessarily have to go through or figure it out some other way. And we also defined the component types. This is how you identify whether, if you split into 3 binaries, then you can, using this component type, you can identify whether you're T, M, or S. And we also defined a O called OEM. So if you have some data or something you want to add to this and distribute it, it's a distribution mechanism also. Primarily FSP, right, it serves 2 purposes. One, we started as an IP container, so to enable the open source enabling model. The second one is also simplify the enabling process. So if you have a silicon and a board, and if you have a socket compatible next generation of sockets, so ideally you swap the FSP. If the APIs are all same, the configuration data matches, you should be able to bring up a new silicon without changing a lot in the board level or platform level usages. And FSP init, this is the 1.0 API, and we made it reserved and make it 0. And this is one of the reasons it's FSP 2.0 instead of 1.2, because we broke the compatibility with the 1.x APIs. So here is from the API wise, you can see some clarification and corrections and simplified this. The primary one is temporam init. Instead of the custom structures, we just made a data pointer, which is the parameters required to configure the temporam initialization. These structures will be defined in the integration guide and based on the implementation of the silicon. And that is expected to change. That's why we use the void. And the second case in the memory init, it had a structure, and that structure had few things, the hub output, the NVS parameters, and other things. What we did here is to simplify that. We took the data as it is, which is the input for that, the data parameterization. And also the output is a hub list pointer. Hub is a simple data structure, as Vincent mentioned, in the memory, which is a gridded. So it has a grid, and it has a, so you can identify the data structure type, and that's uniquely identifies it. So HOB is a terminology from the PI spec, but it's nothing but a data structure with a GUID and a defined structure header. And the tempera minute, and also we said the input output, because it's only input because the outputs are all hobs. So it's kind of correcting the earlier 1.x spec and clarifications. And this is the FSP UPD header. The data is the parameterization data, the signature, revision, and we reserved few bits for future if we need to. But it's pretty much a standard header you'll find on each of the phases, the T phase, M phase, and S phase. That's the structure header. It starts with a signature, and that signature, what the signature value is, will be in the integration guide. And you can see each of the phases. Basically, it has a header and followed by the custom parameters. And for the memory phase, we also defined a architectural UPD that is pretty much a spec-defined UPD parameters, which will be consistent across every generation or every implementation. And that is the details. What are these? And the two things we added, stack base and stack size, is for making the tempera minute optional phase, because whether FSP initializes the temporam or the bootloader initializes the temporam, this phase needs to know what is the temporary memory FSP can consume and use. And the size of it will be defined in the integration guide. But other than that, NVS buffer pointer is the S3 data, which FSP will pass in the previous boot. Bootloader will save and pass it back through this. And bootloader tolum size is for the CBMEM allocations, or if you want a custom memory carved out of the memory allocation, that's the one. So here is the SDK, or this development kit of FSP. So if you're trying to build a FSP or generate a FSP, these are the packages, and package is kind of a folder with a defined structure in the PI spec, which is just additional declaration, and the APIs are defined clearly. So these are the things which are required, like base tools for all the EDK build tools and environment, like Lee and Vincent this morning, they talked about. The MDE module package, it's basically the industry spec defined interfaces or UEFI defined interfaces like hobs, the PI spec, or PCI or ACPI, those things. I mean, even though we don't use ACPI, but all those industry standard definitions and certain implementations, libraries, common libraries, you can call it, those are part of it. And Intel FSP2 package is where the FSP implementations, and this FSP2 package is the new one for FSP 2.0. For the 1.x, there is an Intel FSP package. Both are there. And in this case, we're talking about FSP 2.0, so we just listed the FSP 2.0 SDK, what you need to build FSP. UEFI CPU package is basically the CPU initialization. It's beyond Intel, the ARM also is supported as part of that. Whatever the UEFI spec defines the CPU architectures. In this case, the Intel x86, whatever is defined, is publicly available in the SDM, the software development manual. Those encoding like the MP initialization, certain feature initialization. So we're trying to add more and more silicon initialization, which is publicly available content, the CPU initialization, as part of that UEFI CPU package. That's the new one, which is added as part of the current implementations, so that we can do more and open source. The Intel Silicon package is a concept. There is already a review in the public, and the intention of that is any public specs we can in the Intel Silicon initialization, which is publicly available, and we can publicly post the code. We could add it as part of that. The first one we started is the simple IGD op region. This morning conversation came, is one of the first targets we are adding, like simple interface definitions versus implementations in future. So that package doesn't exist as of today. It will be in a few weeks. What will be there? And the rest is the actual silicon package, which is, let's say, the Skylake as an example. Whatever the Skylake specific implementation, like memory initialization or a few other things which are generation specific, that will go into that SoC silicon package. And that FSP package is more of the glue code, which translates the FSP APIs into the silicon initialization. So today, what we have is all the below 4, 5, 6 packages actually, but whatever you see in the light green is already publicly available. Those are the 2 pieces which is proprietary. Of course, MRC is part of that blue piece. And our goal is to how do we minimize that content and put more into whatever we can publicly. Even though the FSP as a binary is today private and under IP, but most of the content is majority of the content is reused from the open source. And in the upcoming like Kaby Lake generation, all the CPU initialization or majority of it is from the SDM based UEFI CPU package. And what will be distributed along with the FSP is the standard, the binary will be distributed, and the upd.h files for all phases is the configuration and data structures, which are SOC specific. And the integration guide will put together all of this and the details of the policies. And we have got a lot of feedback. Thanks to Aaron specifically for giving detailed feedback. And we're hoping that it's more usable than yesterday. Tomorrow will be much better than today. But BSF file is the boot settings file, which is if you are using a tool like the BCT, the binary configuration tool, FSP contains the static data. So if you want to use that static data to configure the static data within the FSP image, you can use this file as part of the tool. So you can use it through GUI based. And that spec is also published a month back publicly. So the BSF spec is public now. And if there is additional things like GPIO structures and other things will be provided as part of the sample or reference as needed, along with the distribution of the FSP. So here is kind of a high-level summary of the FSP various implementations and where we are. So 1.0 had, I mean, these are a few examples of what is 1.0 based implementations. You can see, I'll use the code names Broadwell, Baytrail, all these things. These are primarily the IOTG defined, and they were productizing it for a while. So the first version of FSP was from Ivy Bridge, which is 3rd generation of, or even 2nd generation. So FSP is there for a while, so it's not new, but it was primarily created for IOTG and embedded segment, primarily to simplify the use cases. And with the Chromebook implementation, we try to bring it into the client mainstream right now. And we are doing the 1.1. We did a Skylake and Braswell. Both of them are implemented in the Chromebooks from the 6th generation and with the 1.1 APIs. And the next generation, which is Kaby Lake follow-on to Skylake and Apollo Lake, will be using the FSP 2.0. And our goal is, since this FSP, Vincent and I co-chair the FSP working group at Intel. So it's not just a client or a specific segment specific anymore. We made it an Intel-wide spec and make sure that maybe in future we'll have the other segments like servers joining this. So if they are productizing it, that will be based on 2.0 going forward. So we're all aligned in 2.0. So 1.1 is in more maintenance phase, and 1.0 is pretty much a legacy and trying to be sustaining phase. And all these images and details are there in the intel.com FSP. You can find the detailed links and other things. So what we are looking is, again, these are like our plans and direction visions. So it's not fully, so we're driving towards that. You can see the trend. How we are trying to do is, first step is like all the FSP binaries we heard from the community also is like, why are we doing it through the web base? So you have to click through licenses and all to download FSP image and all. So first thing is we're trying to change that to just have a Git repo. So we can post these and you can pull them, the latest versions, and sync from them directly. Avoid that web-based link or manually maintain somewhere else. And the second one is the continue to increase the open source content inside FSP binary. And our goal is not necessarily FSP as a big binary black magic where we want to do everything. We're trying to do is, yes, FSP is a package mechanism to deliver, but how do we minimize, but that doesn't mean we can't open source FSP. And Quark is an example Lee and team already did is, even if you have a full open source, FSP doesn't mean that you can't open source. Open source or not is primarily driven by business, IP, legal, all these things. From a technical standpoint, FSP is a mechanism how we deliver it. It's a silicon initialization binary. And in future, the second one is trying to see is the SDK we showed earlier. Can we make it publicly available? Maybe limit the IP portions like memory initialization as the small binary within that, but you can generate your FSP publicly if you have to rebuild for debug purposes and everything. That's where we want to limit the binary size and footprints. And in that way, it's not entirely like FSP glue code. If you see, there is nothing except for UPDs translating to initializing the silicon data structures inside. So it has no IP there. But how do we get there is we're trying to do step by step, making sure we're not missing anything. And these two are the examples where we took that first step of open source content heavily used in the Kaby Lake timeframe. You'll see that UFI CPU package, which is already public and being there. So we're adding more and more content instead of the basic thing what was there. We're adding more and like the Skylake generation, the MP initialization, we're already using it. We are adding more features like SGX and other things which are publicly available as part of the data sheets. We can initialize them and consume them there. Here are the GitHub URLs if you are looking for those packages where they are, and all of them are in the GitHub, Tiana Core EDK2, and the FSP, FSP2 package. And this is the tool I mentioned about which you can use to split it up. But we also added a capability to rebase it. So Aaron, in the past, we need a BCT tool to rebase it. We enabled, extended this tool to support rebasing. So you don't need a BCT, but you can do the rebasing using simple. BCT is primarily now you can do rebase, but also you can do static configuration. But if you just need to rebase to a different address post-build, you can simply use this tool, and it is already available now. This is recently added, and we enabled that. And these are more the links to that, the homepage, intel.com FSP. You'll find all the links and other things, training videos and other things. We all have the FSP 2.0 spec published and the 1.1a, which is the addendum to that latest one. And this is the BSF spec. We also published that firmwareintel.com, which describes the BSF file, how the syntax and layout is. It's pretty much describing the settings. And BCT tool, both Windows and Linux versions are available in the intel.com to download. And we also have a hashtag. So if you're interested to use Twitter, so you can use that. So any questions? And backup, I have the FSP 1.1 boot flows. So you can see the difference if you need to, but sure. Questions? Vincent.
So when you were pointing out the headers that are distributed with FSP, there was one FSP TUPD.
Yeah.
Is that for the 10 prime init portion?
Yes.
So before 10 prime init, well, you technically don't have a stack, so you wouldn't have a C code. What is the purpose of defining an interface in a C header?
So when you build a FSP or when you build a bootloader, right, coreboot as an example, you need to pass certain parameters like microcode if you want to load a microcode, or if you want to say how much size you want to enable or cache certain parameters or things you need to pass it. It is more as a build time, but from FSP, if you consume as a binary, you just bootloader passes a hard-coded, okay, here is the pointer, you link it at build time. But in the cases of SRAM, when you have SRAM, you can run C code there and you can extend it. So basically, at this point, it's only a read-only hard-coded stack, you can say. But in future, when we have SRAM, and especially in the Apollo Lake, Andre might have described earlier, where you have the SRAM available, and you can define based on if you have certain things you want to change on the fly, you can pass them. So it serves two purposes, but it's more as a read-only currently, but we removed that limitation. In future, if you have that, you can use it. You need some data to initialize. Let's say microcode as a simple example. Where do you place a microcode? It's bootloader choice. Yes.
Do we plan to release debug version FSB to the community? I think right now we're only giving the release view, which basically you cannot debug with it, right? You don't see any log
Yes,
proof.
so that is, we are working on that to release debug version along with release version. So far, only release versions are posted. So we're trying to post the debug versions.
From KBake, maybe?
Yes, so there is discussion going on.
Okay.
So it's not about that. It's just to make sure that there is the messages are all sanitized. Nothing more. So it's a debug message. Like it's all about like making sure developers didn't put something they shouldn't. Yes.
So I have a similar question as the thing that just asked. When you, on the HoloLens platform that you sort of SRAM, is the SRAM actually viable? So you can have speculative data segment in
In the Apollo Lake case, it is read-only, Andre, correct me. It is currently read-only, but we are trying to see in the future, at least if we can have behave as a real RAM. So you can read and write. At this point in Apollo Lake implementation, it's just read-only for us.
The FSPO
Yes.
base or component type, is that definition API defined for that? Really?
No, that's meant to be whoever implements it will define it. Let's say if Intel, we define, let's say in secure FSP case, right? We want to put a hash of the FSP and we want to distribute that. We can define in the FSPO, put a sign it and put it in that O component as an example, right? Or if you want to have a data, static data, you want to package and sign it, you can distribute it. There is no, what it defines is FSPO is it has the info header and it says FSPO. Whoever produces the O owns the APIs, whether it's a simple data or you can have code and APIs. That's just purely as a placeholder to do additional things.
Am I allowed to build my own firmware out of it? Question one, is it complete? Can I build a full working image? And the second would be, am I allowed also to distribute it? Can I put it on my blog, whatever?
Maybe you want to take it. I can take the first part of the question. Here, if you have access today, the Silicon and FSP package, the top two packages are under NDA. So if you have access, you can build it. But as we said, the word future direction is we want to make sure that we want to limit those things as binaries. Let's say it has also the PI GOP image, the graphics image, as a binary inside it. So if you have that binary, you can rebuild the code. So as I mentioned, Glue Code doesn't have any APIs or anything. It's just we need to go through the process and make sure that we can. Our goal is to make sure you can build it, and majority as much as we can still open source it. The next question.
Right. I think and this is tease off of what we talked about at lunch, right? So essentially what you want is, this is more a legal license question of, if I grab fsp.bin off the web, mix in my coreboot recipe, and want to post the resultant binary, is that permissible? I believe that's the intent. I'm not a lawyer. I've heard in the past the present FSP, the click through the end user license agreement, maybe people, it wasn't as clear, but the intent is that. But I'm a technical guy, not a lawyer, but the intent is most definitely what you would like to do, which is be able to derive resultant product from this, including full firmware images, and redistribute. The whole intent of this program is remove the need to do sign NDAs and other things, grab content off the web, build your product, and do with as you will. But I'm not a lawyer. And one of the action items we can do, if that is a concern, is talk to people who know more and about the license, specifically the GitHub posting. We want to get rid of the click-through and put the license.txt next to it, such that you can use source control, but also talk to the people who are smarter on licenses and the law to make sure the intent, which I expressed just now, is truly the case. But I believe that is the intent. But we will follow up as part of this Git posting to make sure the license.txt appropriately reflects that. That is the intent.
Giri, there were questions from the community earlier about postcodes in FSP.
Yes.
What is the plan? Like, are you planning to put
So
up a
the
document?
postcodes are there, and we are defining. I mean, those are captured as part of the integration guide, at least in the KB Lake, as we know. In the Sky Lake at prior, yeah, we didn't pay attention, or we didn't do that as part of, as I said, right? We are improving and getting the feedback what we need to do. We also did standardize the postcode, at least the 16-bit split into various, so you can identify which API you are in and what we are doing on a very high level, and within that the details, so that at least it's consistent. So you don't have to decode every time looking to integration guide, but at least you could decode where it is. But within, like, let's say if you find you're in memory code, you're hung, at least what you are doing when you're hung is the details you may need to look into integration guide, but at least it's easier to say that whether you're hung inside FSP or in the bootloader once we return it, or where we are, at least to simplify that debugging. So the postcodes will continue to be enabled. We are also looking at enabling like a cataloging the debug messages to reduce the size. One of the negative side of the debug FSP is the larger size. So it depends on how the firmware is allocated. You may optimize for a release production. You may not fit in the standard firmware problem, right? So if you want more debug, you do that. So what we're trying to do is use the cataloging capability. So at least you encode it during the build process, but you have a catalog schema file, which will be, you can decode it at the receiving end.
Right. You print message one and then
Next one.
offline have
Decoder to do that.
big string.
So at least in the release model, if you're doing some timing issues and all, that should really help, because debug, you may not find or reproduce those issues.
So for this, I guess, FSP open binaries, are you imagining that, what do you envision the interface if you're building the FSP to the memory init will be? I guess, like, let's say that I need some additional parameter to the memory customization that is not brought out through BCT and through the UPD. Is your envision that you will try to expose the entire common code, reference code interface to memory init, or are you imagining that that will be an additional wrapper, or I guess not defined
Yes,
yet?
so the question is, yes, if it is fully open, like let's assume the case where it is not IP content, right? So in
Right.
that case, you can technically add your own parameter or extend your parameter to do that needful, but it won't be a standard. So it's just kind of a test version, right?
Right.
If you need that extension, I would like to get that request so that we can review that and see if there is the other way of doing it, or is it like we really need to add one more parameter to customize to meet your use case,
Right.
and we will add that.
Okay.
So basically, if everything is open, you can technically add it, but
Right.
still it's not preferred, because when you get a next version of FSP, that
Then you have
will
to
be
make-
missing. But for test purposes and other things, you can add it.
Okay.
And we would like to get that request so that we can analyze that and we can make it part of the next releases. So you don't have to do that hacking.
Okay.
To do that.
I guess if I understand correctly, your thought is that maybe you could allow some sort of building of the FSP, and you'd give like the binary for just the memory init code and the wrapper, right? Is that
So basically, that's what the vision we said, right? The future we want to see is like you can build FSP, but only the IP container pieces may be the binaries.
Right.
In the ideal world, like Quark, you don't need any binaries. You can
Right.
build everything from open. But if we can't, because of all the legal stuff, we don't want to stop. That's what we see that the biggest missing piece was. We stopped at, we can't open up all the silicon initialization. We stopped there, right?
Right.
So with FSP, what we are trying to do is, okay, let's take the silicon piece away. Let's look at the around things, whatever we need to do to open source it. Maybe simple things as GPIOs or reset or SMMs or other things, or ACPI for that matter, which could be publicly done. Once we take out all those things, then we can focus on the silicon piece. So we are doing both parallelly.
Okay.
While we bring up the bootloader with coreboot and EDK2 parallelly, and the Braswell is the example Vincent and Lee mentioned this morning, is the EDK2 version of the Braswell is also FSP based one is open source now. Right. So we're trying to continue that trend, whatever we can, when we can.
Okay.
But then continue to focus within FSP is how much we can do open source. That's the UEFI CPU package, Intel Silicon package definitions.
Right, and the hope is keep the FSP just SoC specific memory in it. So hopefully there will be a rich enough set of UPDs, for example, that cover what you want. And if you're doing something really weird and are off the reservation, hoping that's the outlier, right? Make FSP just what the SoC's memory controller exposes and all the different permutations on how the board could have been wired up, et cetera. Anything that's system board vendor degree of freedom exposed through things like UPD. And if we got it wrong in some places, and we definitely like feedback, let us know. But we want you just not to have to sweat that part of the platform bring up. It's just magic the SoC does. It's a minimum amount of code that's SoC memory controller specific, for example. And it should be parameterized with things like UPD, what's board specific.
Okay, so your goal is to, so I guess there's room to define how this SDK will deal with the binaries and explicit.
Yes, so as long as the API is maintained, the goal is you can drop in, right? So you can drop in into one project, one platform versus other board level implementations. So if the APIs are modified or customized, you have to continue to customize it. That's not necessarily the intention is because FSP is also what we test and validate it. So you get the benefit of just dropping in and it works case.
Yeah.
Cross your fingers.
So one of the documents that's available is the BIOS Writer's Guide for each of the CPUs. What is Intel doing with regards to the FSP integration guide to describe what is being done within FSP and what actually needs to be done in the BIOS?
Yes, good question. And that's part of the integration guide enhancement. Basically, what we are looking is whatever that needs to be done by bootloader, right? Whether it is coreboot or EDK2 outside of FSP, we want to document that in the integration guide. So you know what exactly needs to be done, the prerequisites and what needs to be done before you call API or what needs to be done post that. Like if there is a data we pass, you need to describe what data we pass, whether using it or not using it should be a feature or an option for the bootloader. So goal is FSP integration guide may turn into the mini BIOS writers guide, call it, whatever we don't do inside the FSP, what needs to be done bootloader. And that needs to be publicly defined. And one of the challenges is the reset thing, right? Other than the standard hard reset, warm reset, cold reset, there are certain like custom resets we have to do for ME, handshakes, and other things. So those needs to be now defined so that bootloaders can use them. Yes.
Yeah. So the 2 point, I guess for boards that don't need that, I guess is your main thought that even if the board doesn't need to boot from MMC or might not even have that support, that you would still distribute it as 3 binaries or still be divided into 3 binaries for the
you can combine into a single binary and you can rebase into one place.
Okay.
And so basically it is like you have a flexibility. We will rebase it as single binary. So we'll rebase it there. So the tool will allow you to split it. And you can individually rebase that if you need to place it at a different locations to optimize the flash layout.
Okay.
You have that flexibility, and that's what the tool specially highlighted in the previous slide. The split FSP bin will allow you to do that. It's just a simple Python script to just chops the binary and just rebases that.
Okay, so distribution method will be 1 binary and then.
And it's a one rebase, and we'll say what is default rebase. So if you can place it, you don't have to do anything, but this will allow you to do it.
Any other questions?
And one other point is we are also trying to use FSP as a default mechanism for internal use also, FSP plus EDK2, of course, in our case. In that way, at least the FSP you get is already tested along with our silicon bring up and other things, as opposed to in the previously, we tried to do that FSP as a secondary project because we're just bringing up and the primary focus is on bringing up a silicon, and which is already done in the EDK2 style. So we're trying to combine that both so we don't have to do 2 different things. It's the same from a silicon initialization, it's just the packaging. packages FSP use in EDK to deliver it, so it can be used everywhere.
Is that for all chipsets, for the whole Intel range, also for the server platform?
Server is open, so they are not yet any official commits or anything. So I'm from client, I can speak for client. Yes, for all the future client platforms and IoTG side, whatever we produce will be based on FSP. And server side, it's basically business thing, ask customer need and demand. So.
For what it's worth, though, I've been trying to get the server side to sign up for FSP, so if you're also interested, please ask for it, because I'd like to have more people ask for it. It'll help them decide to do it.
So Duncan has a request for it, and if you have a need, yeah. I think it's not like they are opposed. It's basically they're looking for a business justification and putting the resources in the right spot. So, as we mentioned, it's just packaging, right? So it's not like, I mean, anybody can do that if you have access to the source. It's just more of packaging and then supporting and doing that. So in the client side, at least, we have the whole team here, Robbie, Hannah, Andre, and all. So they're engaged and supporting that. So in that server case, they need to be funded and so.
Do you have any plans to do TXT or any other proprietary security measures supporting FSP?
TXT, you mean? Yes, in the Skylake, we didn't do that for all because we are doing whatever is needed for the Chromebooks, like basic things, what is needed. So in the KB Lake and future, right, we're trying to do a full-fledged usage of FSP. That means all the features are available. You can turn on, turn off it. The negative side is the size. So we need to work on, like, do we need to slim it down if the size becomes all the features enabled? Then if you have to reduce, then we may have to do a bit which does the base certain set features and maybe a corporate version, consumer version. So that could be a different based on the need. But we don't want to create multiple versions. But if that means we have to do that, we'll look into that. Yes, the TXT feature will be there along with SGX and other new features and technologies.